Okay, so today's Leeds code problem is a dynamic programming problem. It's the famous climbing stairs. So to summarize the question we've got is as input, we have an n integer variable which represents the number of steps in a staircase or the number of stairs. We will start at the zeroth stair or at the beginning of our staircase, and the goal or the target is to reach the top of that staircase. The only condition we've got is we can either go up one or two steps every time. So the simplest way to do this is by doing a brute force. So brute force method, which I mean we can just represent all the possible routes we can take in a recursion tree in order to reach the target or the top of our staircase. So we've got, for example, this staircase that has 5 total steps. So our n is gonna be 5, and to represent it, I mean, we're gonna start here, and we want to reach this destination. And one mistake that could be done, even though this is an easy discourse question, one mistake we could do is actually calculate the number of steps, which is not the target, it's not the goal of this question, but what we need to return is the number of routes or number of ways to reach the destination. So we can go, for example, like this. This is the one step at a time, right? Or we can go, for example, like this, or any different ways. So this, all of these steps is gonna be considered as one. Also, the second way is gonna be considered another one. To represent this, we will use two variables, variable I and variable n. So I is going to represent the current stair or staircase, the current step, and the n is our target. So we'll start at 0 and we'll go, for example, we will use 5. So at each step we will go either 1, same goal, or we can go 2, another new goal. Another way is 2, 5, we can do 3, 5. Here we can go 3, 5, 4, 5, for example. And we keep going. We do the same thing for every node of our recursion tree. Each time, or every node, we'll increment it by 1 at first and by 2. So here we can say we have reached our destination. Same here, we've got 4, 5, and then 5, 5. We got the same values here. And finally 5, 5. Also 6, 5, even though 6 is going to be bigger than the destination, so we're not going to calculate it. So we still have this one here, so it's 4, 5, 5, 5, and finally another 5, 5. So if we calculate the total number, we've got 1, 2, 3, 4, 5, 6, 7, and finally 8. So when we got n is equal to 5, we should have 8 distinct ways to reach the target destination or the top of our staircase. To put this in a programming, we will do a stopping condition. So we will go. We need to define our inner climb function, which will take I and n, right? The stop condition is gonna be if n is bigger, if I is bigger than n, just return 0, that doesn't count. For example, when we had 6 of 5, then we have overreached the staircase, so it doesn't count. Or if I is equal to n, then we have reached our destination and we can just return 1. So here is the recursion call, return inner climb what's I plus 1, n is the same, and inner climb of I plus 2, this time n. and then we should actually call our function. So we go inner climb, we start at the zeroth or at the beginning of our staircase, and we go towards n, and we should return this. Obviously, since we're gonna do brute force, it's gonna give us a time limit exceeded if we submit it. So the first step of optimizing our solution is going to be to using cache or memoization. So to use memoization, first we will define our memo array. I mean, the idea behind the using memoization is that, as you can see here, we've got 3, 3, 5, and 3, 5 again, 2, 5, and 2, 5 again. So if we already calculated this value, or we know what is the end results or the total number of routes that reach the target step, starting from 3, 5, there's no need to recalculate it or to make the recursive call here. Because instead of making the recursive call, what we're gonna do is we're gonna create a memo array or a cache that has the size of our staircase, and as you can see, sometimes we reach n plus 1, so it's gonna be actually always start with 0. It's gonna be times n plus 1. So the memo array is gonna be all zeros right at the beginning, and it's gonna be size n plus 1, because sometimes, for example, in the previous page we had 6 of 5, and we will update the signature of our function. So we've got memo. Also here we will call our cache array. We should actually use it here, so if it exists, if it's not 0, if memo of I is not 0, all you can do is bigger than 0, return memo of I. And we should, so we are using it, but we should actually update it. So memo of I is equal to this value here, the recursive call. And instead of redoing the calculation, we just return memo of I. And we know that the memo of a certain step, or the memoization of a certain step, will only be updated at when we reach the end of our staircase, because we keep calling inner climb, inner climb. When we update this value, it's only gonna get very different from 0 when we reach the end of our recursive call of these both parts. So we know that this should work. We do run. I mean, no, it did not work, because, let me check, missing one required memo. Okay, forgot to add memo. We should pass our cache, and this should be, okay, so this right now this works. If we look at the time complexity, we had a recursive tree. It was big O of n, or big O of 2 to the power of n. Now this one is gonna be big O of n, which is so much faster, but uses a lot of memory. So we do submit again just to check how much. It's 30% better, but it beats 30% of questions of solutions. So, I mean, we've got the memoization. What we need to do is actually use dynamic programming. So, in dynamic programming, as you already know, we'll define a function of an array, dpi, which is equal to, similar to our memoization. The only difference is we're going to be using different. dp of 1 is equal to 1, right, and dp of 2 is equal to 2. Now, for I in range of n, dp of, I mean, we start at the third, dp of I is equal to dp of I minus 1 plus dp of I minus 2. Return dynamic programming of n. So the main idea we got here is, for example, if we had an array of dp of type 1, 2, 3, can do 4, 5. At each step of the way, I mean, this will represent staircase of size 1, 2, 3, and so on until we reach the last step, which is 6, right? So how many different ways can we go from 0 to 1, only one way, right? So we update dp of 1, now it's equal to 1. How many different ways can we reach dp of 2, or the target top of our staircase is going to be only 2, so we can go from 0 to 1 and 1 to 2, or we can go directly from 0 to 2. So we've got 2. And for our third case, it's just going to be the sum. So 1 plus 2 is going to be 3, and the fourth step is going to be 2 plus 3, which is 5, and so on. We got here equals 8, and finally 13. So this is the one we calculated earlier. dp of I equals of dp is equal to 0 times. What is the mistake? So we've got dp of 1 equals to 1, dp of 2 equals to I, so this should be n plus 1. Just a small mistake because n is not included in Python, you know. So submit. And we got one edge case, which is if n is equal to 1, in that case just return 1. Because what just happened is we're trying to update dp of 2 even though the size is not, there is no third no third memory place in our array. So we go run, submit. This is correct. I mean, it's what, how much? 20% improvement. We submit it again. Now it's even more better, so much better, and it's as fast as possible, I guess. We can also even make it even faster by using a Fibonacci number calculation, because at each step we use the previous two values to calculate the third value. So we'll have 3 variables that will be updating many times until we reach the target of our question. So we can do like, we can keep if n equals to 1, return 1, right? And we will do first is equal to 1 and second is equal to 2, right? For I in range of n. We can do third is now equal to first plus second, and in the next step of our loop we will do first is now equal to second, and the second is equal to the sum, which is third. And finally, at the last step, I mean, we shouldn't repeat the same mistake. At the last step, we do the second and the third values are going to be the same, so we just return second. We'll run it. Ooh. First is 1. Oh, yeah, small mistake. We start from the third value, and we submit it. So now it is as fast as possible, and it uses so much less memory than previously. We've got only 3 variables here, so let's do it again. Yeah,